Okay, today we'll start the testing of hypothesis. In previous two lectures, in first lectures we have discussed about the testing of hypothesis and as an introduction, and we also discussed in our previous lectures Z test and students T test with T distribution. So today this is the third part, and we will study about the F test, capital F test and chi-square test as a part of testing hypothesis. Okay, variance ratio test or capital F test, also called Snedeker's variance ratio test. Okay, in testing the significance of difference of two means of two samples, we assume that two samples come from the same population or populations with equal variance. That means variance will be equal for population or sample. Two samples may be same for the population. So the objects of the F test is to discover whether two independent estimates of population variance differ significantly, or whether the two samples may be regarded as drawn from the normal population having the same variance. Okay, so hence before applying t-test for significance of the difference of two means, we have to test for equality of population variance by using f-test. That means we have to apply f-test for to test the equality of population variance. Remember, but in t-test we apply this for two different means or for two different variants. But in f-test we have to test the equality of population variance. Let n1 and n2 be the sizes of two samples with variance s1 square and s2 square. The estimation of population variance based on the sample s1 square will be n1 divided by n1 minus 1 s1 square. Okay, and s2 will be like this. The degrees of freedom b1 n1 minus 1 and second one b2 will be n2 minus 1. So to whether the estimates the s1 square and s2 square are significantly different, if the sample may be regarded as drawn from the same population or the two population with same variance. That means there is a two conditions: must be same population and the same variance. Variance will be equal for that. That means we have to set up first of all null hypothesis. We have to set null hypothesis is not sigma 1 square first variance equals to sigma 2 square equal to sigma square. That means all variance are equal for the null hypothesis. That is, the independent estimates of the common population do not differ significantly. That means there is no difference, common difference between the independent estimation. So to carry out the test of significance of the difference of the variance, we calculate the test f test, capital F, equal to s1 square divided by s2 square, this ratio. Okay, the numerator is greater than the denominator. Numerator must be greater than so conclusion or comments: if the calculated value f exceeds at 5% significant for the degrees of freedom n1 minus 1 and n minus 1, the degrees of freedom given in table, we conclude that the ratio is significantly at 5% level. Understand? If s1 is greater than f2 square, then f exceeds this, that means the calculated value will be greater than table value. Okay, so we conclude that the sample could have come from two normal population with some variance. So the assumption, there are three assumptions for a capital F test. The population for each sample must be normally distributed, and second one, the sample must be random and independent. Okay, so the ratio sigma 1 square to ratio 2 square, that means sigma 1 square divided by sigma 2 square should be equal to 1 or greater than 1. That is why we take the larger variance in the numerator of the ratio. That means in the variance numerator, first variance, first for the first variance of first sample will be greater than. So application, there are many applications of F test. In first lecture we have studied about the application of F testing of hypothesis. So there are two important application for capital F test to test whether two independent sample have been drawn from the normal population with the same variance sigma square, whether the two independent estimation, it estimates the population variance are homogeneous or not. That means if they are same or not, you can test with applying F test. Now let us consider some example. Suppose example 1, two random samples drawn from two normal populations are as follows: first sample A and second sample B. Okay, so test whether the samples are drawn from the same normal population. That means you have to test the same normal population. That means you have to apply capital F test, whether it is the same or not, or homogeneous or not. You have to test. The first solution, two tests of two independent samples have been drawn from the same population. We have to test first of all equality of the mean by applying t-test, and secondly equality of population variance by applying capital F test. So since t-test assumes that sample variance are equal, we shall first apply the capital F test. Understand? Now capital F test, null hypothesis will consider equal. Variance will be what? First sample variance and second sample variance will be equal for null hypothesis. That is, the population variance do not differ significantly. That means there is no difference between two variance. Understand? This is considered as null hypothesis. So alternate hypothesis will be opposite. That means alternate hypothesis S1 will be not different. That means not not equal. That means different. Okay. So capital T test will be capital F equals to S1 divided by S2 square, where S1 is greater than S2. Now computation for S1 square and S2 square for two individual variant in individual samples. First X1 is this, first from where? First sample. Okay, and this is the second sample, but one sample less than first sample. So we can calculate the mean X1 bar. Okay, X1 bar, what will be? Taking sum, then divided by what? 1 2 3 4 5 6 7 8, dividing by 8, because first number of sample in first space what? N1. So X1 bar will be 21.625. Understand? This is the X2, and this is X1 minus X2 whole square, and this is X2. X2 minus X2 bar. X2 bar means what? Taking sum divided by 7. Okay, then X2 minus X2 bar will be this, then taking a square, we get the last column. So X1 bar is this, and N1 equals to 8, and summation X1 minus X2 X1 whole square, X1 bar whole square equals to this one. That means sum of squares of difference. So X2 bar equals to this, and N2 also 7, 1 is less than first sample, and summation X2 minus X2 bar will be 182. So X1 square equals to what? We must know for the population. For population, we get summation X1 minus X2 on a whole square divided by N1 minus N2. Okay, so this square divided by 7, N1 minus 1 equals to what? 7, 8 minus 1. This is why we get this. And S2 square equal to what? For the second sample, taking sum of the square of the difference, N2 minus 1, this will be this. So S1 square is greater than S2 square. That means capital F is greater than 1. Understand? Greater than 1. So the table value of F for degrees of freedom, first sample 7, and for the second sample 6 degrees of freedom at 5% level is 4.21. Okay, from the table actually we get this one for the capital F test. Understand? This is the chi-square test, and this is the value of F test for the degree of freedom 7. Okay, 7 and this is the t-test. This is the table for f-test. For the first sample degrees of freedom 7 and here 6. Second sample what? 6. So value will be what? 4 to 4.28. Understand? Sorry, 4.21, right? For first 7 and second sample 6. 4.21. Understand everybody? Table value got? Hello? First sample 7 and second sample 6. This is the table value for capital F test. 4.21. Okay? So from 4.21, understand? For the first sample, first degrees of freedom 7 and second sample degrees of freedom what? 6. We get table 4.21. So the calculated value capital F is less than table value. Understand? So null hypothesis is accepted. If greater, so if less, then accepted. Remember it. If since this is the less than the table value 4.21, this is why null hypothesis will be what? Accepted. Hence, we can conclude that the variability of two population is same. That means we accepted the null hypothesis. Understand? Now t-test for the null hypothesis. We now will try to test this for what? Applying capital t-test. Null hypothesis is what? For what? T-test will be test whether a mean will be variate or not. Mean will be difference or not. That means the population are same in mean. The population mean will be equal is the null hypothesis. Alternate will be what? Not equal. So test statistic for t distribution for two different sample. This is the formula. We have applied this t-test, student t-test in our previous lecture. We have finished many examples applying this. So just from table putting the values, and 1 equals to 8 and 2 equals to 7 and minus 2 equals to, we get this. So s equals to what will be square root of this 5.796 from calculation. Now t equals to, this is the formula for two individual sample, x1 bar equals to x2 bar equals to this. Now s equals to what? Standard deviation 5.796. 0.9702 variate to what? Degrees of freedom what? N1 plus N2 minus 2 difference. Since N1 plus N2 what? 8 plus 7 15. 15 minus 2 what? 13. Degrees of freedom 13 difference here. So for students t distribution for degrees of freedom 13, the table value is what? 2.16. But it is more and more less than 2.16. That means the calculated value of t is less than the table value. So H naught is, null hypothesis is accepted. That is, there is no significant difference between the population mean. So there is no difference in population mean. Remember it, mu1 and mu2 is population mean, but x1 bar, x2 bar is sample mean. There are two difference between mean. One is sample mean, other is what? Population mean. Population means whole sample. So we conclude that the two sample have been drawn from the same normal population. So applying capital F test, we have tested the variance is equal, and applying t test, we have tested what? Population mean is equal. Now another example, two independent sample of size is 7 and 6. First sample size n1 equals to 7 and n2 equals to what? 6. So first sample A, this is given, and second sample B also. Estimate whether the sample have been drawn from the normal population having same variance. We have to test the variance whether it is same or not, applying capital F test. Now H naught is the null hypothesis. The variance are equal. We have considered for null hypothesis. That means the samples have been drawn from the normal population with same variance. We have taken as null hypothesis. Now alternate hypothesis will be not equal. So under this null hypothesis, the test you have to test a statistic capital F will be what? S1 square divided by S2 square, where S1 greater than S2. Now compute S1 square and S2 square, we have to tabularize the sample. First sample X1 and second sample X2, then taking a difference with X1 bar. How we will calculate X1 bar? Taking all sum divided by 7, we get 31. Okay, so this minus 31, this 30 minus 31, this 32 minus 31, this. So X1 minus X1 bar will be this. Now taking a square, we get this one. Taking sum. Now X2 second sample and difference X2 minus X2 bar, for every sample we get this, and square will be this. Sum will be what? 26. So S1 square will be what? Summation, sum of the squares of difference of first sample. Okay, n1 minus n1 will be give 4.666. Now S2 square will be similarly for sample second sample 5.2. Now capital F value what? 1 point something. That means S1 is S2 here. S2 is greater than, right? Clearly observe, S2 is greater than here. Understand? To take this value, we have to take an S2 sample greater 5.2. 5.2 we have to divide this by this. Then S2 is greater than where. So the tabled value for degrees first sample, degrees of freedom of first sample 6 minus 1, that means 5. And second sample, degrees of freedom what? 7 minus 1, that means 6. At 5% significant level, what? 4.39. Since the tabled value capital F is less than the calculated value, so null hypothesis is what? Accepted. So there is no significant difference between the variance and the sample mean. That means this 4.39 comes from how? First sample degrees of freedom 6 minus 1, that means 5, 6. Understand? 5, 6. So from this table 5, this is the 5 first sample, and this is the 6. This is the 4.39. Understand everybody? 4.39. This is the first sample 1, 2, 3, 4, 5 degrees of freedom, and second sample what? 6 degrees of freedom. This is the common. This is the common, right? Intersection of both degrees of freedom 4.39. So we get the value for what? One S2 is greater than S1 square. So we get 4.39 from the tabled value. Since the tabled value of F is less than the calculated value, so null hypothesis is accepted as the previous example. So that is, there is no significant difference between the variance. The sample have been drawn from the normal population with same variance. Okay. Similarly, for example 3, the two random samples revealed the following data. First sample this, and size what? 16. Second sample size what? 25. Mean given, mu1, mu2, and variance also given. Test whether the sample come from same normal distribution. Okay, there we have to apply both test. We have to apply mean is equal or variance is equal. For two tests, the mean is equal. We have to apply t-test, because t-test can test the mean whether it will be equal or not. But for test variance whether it will be equal or not, we have to apply capital F test. Remember it. So normal population has to be parameter, namely the mean mu and the variance sigma square. So to test that two independent sample have been drawn from the same normal population, we have to test what? The equality of means and the equality of variance. So for the first equality of means, we have to apply t-test, small t-test, student t for t distribution. Apply. Now capital F test for null hypothesis, they are equal. Considering null hypothesis is not what? Variance is equal. The population variance do not differ significantly. Alternative hypothesis will be what? That means they are different. Under the null hypothesis, the test will be S1 square divided by S2 square. Because first standard deviation, standard variance S1 square, and this is the S2 variance, second variance. Now we have to consider S1 square divided by S2 square. Now N1 given, N2 given, S1 square given, S2 square given. Okay. So capital F will be what? Value S1 square divided by S2 square equal to what? N1 divided by N1 minus 1, N2 divided by N2 minus 1. This comes from where? Capital F test formula. Now applying this, we get actually 0.9752. Understand? The calculated value of F test 0.39752. That means the tabled value of F at degrees of first degrees of freedom 16 minus 1, that means 15, and 25 minus 1, that means 24 at 5% significant level will be what? 2.11. From table it has come, previous table. Since the calculated value is less than that of the table value, so null hypothesis will be what? Accepted, and there the variance is same. Now for t-test, similarly, to verify whether the population mean is equal or not. So considering null hypothesis, they are equal. Population mean are equal. So alternative hypothesis will be what? Not equal. Now given n1 equals to this, n2 equals to this, and x1 bar equals to this, x2 bar equals to this. This is given in table. Okay, x1 bar, this is the mean x1 bar, and this is the x2 bar. So applying the formula, standard deviation for t-test, s square equals to, this is the formula, we get 43.333. So s equals to, taking a square root, we get 6.582. Now applying t students t distribution formula, we get what? Negative values. And for n1 plus n2 minus 2 difference, that means this is the degrees of freedom for t-test. The calculated value of t, absolute value of t, that means 9.490. The table value of t, 39 difference for 5% significant level, 1.96. This comes from which table? Students t distribution table. Understand? For what? 39 degrees of freedom and at 5% significant level. So this is more and more larger than the table value. So since the calculated value is greater, more and more greater than the table value, so H net is what? Null hypothesis will be rejected. If more greater than the table value, must be rejected. That means there is no significant difference between the mean. That means it is accepted. Alternative hypothesis will be accepted. The alternative hypothesis will be what? They are not same. Since there are significant difference between the means and no significant difference between variance, so we conclude that the sample do not come from the same normal distribution. That means they have come from where? Different normal population. Different from normal population. So 1, 2, and 4 example. 1, 2, 4 example will be homework. 1, 2, 4. Everybody write down. This is very important example for you. Using the example, you can do this exercise assignment 1, 2, and 4. Now another important distribution, actually chi-square distribution or chi-square test. Okay, you have to apply this chi-square test. When a coin is tossed 200 times, suppose we have a coin, there a head or tail. Understand? So we are tossing this how many times? 200 times. The theoretical consideration lead us to expect 100 heads or 100 tails after 200 times. But in practice, these results are rarely achieved. Understand? Heads may be more or tails may be more than heads. But in practice, the results are rarely achieved. So the quantity chi-square, a Greek letter, is pronounced as chi-square. Describe the magnitudes of discrepancy of between theory and observation of. If chi equals to 0, the observed and expected frequencies completely coincides. That means the greater the discrepancy between the observed and expected frequencies, and the greater is the value of chi-square. So chi-square affords a measure of the correspondence between theory and observations. Now, for observations, suppose the total number of observations ui, okay, I equals to actually 1 to n. Many observations here. This is the natural number. Y is a set of observed values, frequencies, and capital EI is the I equals to 1 to n, the corresponding set of expected frequencies. So chi-square is defined as chi-square equals to summation I equals to 1 to n ui minus ei whole square divided by ei. This is the chi-square formula, where summation y equals to summation ei equals to total n, total frequency, capital N, remember it, and degrees of freedom will be n minus 1. N is the total number of frequency. Now there are two conditions. If chi-square equal to 0, the observed and theoretical frequencies agreed exactly. If chi-square greater than 0, then do not agree exactly. These two conditions we must remember for this, and this is the chi-square formula. Now application of chi-square test. Chi-square test is one of the simplest and the most general test known. It is applicable to a very large number of problems in practice. That means if sample size are more and more larger, okay, so which can be assumed up to under the following heads. As a set of goodness of fit, we can apply chi-square test as a test of goodness of fit. After this class, we will try to understand this about this goodness of fit. Very important. As a test of independence of attributes, okay, we apply to test the independence of attributes as a set of homogeneity of independent estimates of the population variance. We can test the variance population as a test of hypothetical value of population variance. This is the population variance as a square. As a list of homogeneity of independent estimation of the population correlation coefficient. That means there are 5 applications for chi-square. Now, conditions for applying chi-square test. Uh, Conditions, there are three conditions actually. If the total number of sample n should be at least 50, capital N is the total 50, then the small number of cells. So the theoretical cell frequency should be small. Here again it is difficult to say that the continuous smallness, but 5 should be regarded as the very minimum and 10 is better. If the sample theoretical frequencies, that means less than 10, then difficulties is overcome by grouping 2 or more classes together with. Actually, we will understand this when we study the example. This is the chi-square distribution formula. For large sample size, we have to apply this sampling distribution, specially named as chi-square distribution. This is the formula: C chi-square over b minus 1, b by 2 minus 1, e to the power x square by 2, where e equals to this and b is the number of degrees of freedom and c is the constant, depending only on degrees of freedom b. This is the formula for what? Chi-square distribution, and this is the definition of chi-square distribution, and this is applied for the what? Large sample size. Now, chi-square test as a test of goodness of fit. So chi-square enables us to ascertain how well the theoretical distributions such as binomial, Poisson, normal, we have and fit empirical distributions or distributions obtained from the sample data. Actually, we have studied in our previous lecture binomial, Poisson, normal, etc. Okay, in probability distribution. but actually we are testing the hypothesis by applying what chi-square test. Now let us discuss the example depending on chi-square test. First of all, example 1. The following tables give the number of accidents that took place in an industry during the various days of the week. Test if accidents are uniformly distributed over the week. Okay, we have to test about the accident if it is happened regularly. Okay, whether it is happening regularly or not, we are testing this. Okay, day in a week given: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. A number of accidents given here. Okay, in big industry, maybe the sample of the a big industry. So this null hypothesis is not. We have considered the accidents are uniformly distributed over the week. That means we have taken the null hypothesis. That means we have taken the accidents are happening regularly. Okay, and that on that week. So H naught is the null hypothesis. So under this null hypothesis, expected frequency of the accidents on each of these days. How many days here actually? 6 days. One day will be closed. That's why. So total accident what? Total after taking addition we get what? 84. So the expected frequencies of the accidents on each of the days will be 14. This is the actually mean. So observed frequency what? 14, 18, 12, 11, 15 and 14. This is the given. Okay, given frequency accident. And expected frequency what? We expected is 14. Understand? Just we have taken what? This mean average. So if we take this y observed minus expected and square and taking square. Okay, 14 minus 14 0, square 0. So 18 minus 14 what? 4. 4 square equals to 16. 12 minus 14 what? Minus 2. Minus 2 whole square what? 4. 11 minus 14 equals to what? Minus 3, right? Minus 3 whole square what? 9. 15 minus 14 what? 1. 1 square means 1. 14 minus 14 equals to 0. 0 whole square means what? 0. So if from the table the values we have to put on the formula of what? Chi-square is equal to summation y minus ei whole square ei. Here summation I equals to 1 to what? 1, 2, 3, 4, 5, 6 sample only. I equals to 1 to 6. Understand? I equals to what will be? 1 to 6. Just putting this summation. Summation we have to take sum. Take summation of this. Summation means this what? Adding this 16 plus 4, 20. Okay. 20 plus 9, 29. And this will be on 30. So 30 divided by ei means what? Expected frequency 14. So 14. This will be what? 2.1428. Now conclusion. Table value of chi-square at 5% significant level at 6 minus 1 degree, that means 5 degrees of freedom, 11.9. Actually you can take the over the table. This is the chi-square table. This is the chi-square distribution table. So for degrees of freedom, what? 6 minus 1, that means 5 degrees of freedom at 5% significant level. 5% significant level what? 11.070. Understand? At 5% significant level at 5 degrees of freedom, what? 11.070. Understand everybody? Hello?
Yes, sir.
Okay. Just putting these values, we get the what? Table value. So 2.1428. And the table value is 11.09. Since the calculated value of chi-square is less than the table value, so null hypothesis accepted. If less than, always remember, if less than, accepted. If greater than the table value, then rejected. So we have considered that the accidents are uniformly distributed over the week. That means in every week, continuously the accident are happening. Understand? We have proved with an experiment and with the test of what? Chi-square. Now another interesting example 2. A die is thrown 270 times, and the result of this throw are given. Number of appears in die. There are six parts in die. You must know 1, 2, 3, 4, 5, 6. Die means you must know. So in first frequency, 1 comes how many? 40. 2 comes 32. 3 comes 29 times. 4 comes 59 times. Understand? 5 comes 57 times. 6 comes 59 times. How many total times? 270. Test whether the die is biased or not. Somebody get always 6 in Ludo game. Understand? So this is by we are testing it is biased or not. So under H naught, null hypothesis, the expected frequency for each digit, you have to divide the total number of thrown 276 divided by 6. There are sample what? How many samples? 6 samples. Only 46. So every part on die should come 46 times. But we are testing this to find the value of chi-square. First observed value what? Observed value 40, 30. Second row is the observed value. Okay. Now expected value what? 46. Expected value 46. So y minus ei whole square. That means difference whole square. This as the previous example. So applying the chi-square formula, summation y minus ei whole square divided by ei. Total this total sum what? 980. After calculation with calculator, we get 980 divided by observed expected what? 46 for every sample. 46. Now we get 21.30. But at 5% significant level for 5 degrees of freedom, we already have seen that 11 table value what? 11.09 in previous look like previous example. So since the calculated value of chi-square is more and more greater than greater than table value, so null hypothesis is rejected. That means die is not unbiased or die is biased. That means not biased means what? Biased. The die always biased. Some in the game, some always get 6. Okay, some always get 1 this way. But if anyone expect 1, they did not get it, or maybe late to get. Okay, similarly, the following table shows the distribution of digit in number chosen at random for a telephone directory. Okay, digits will be this. How many digits here? Actually 10 digits. Frequency this is the telephone number digits. Test whether the digits may be taken to occur equally frequency in the directory. You have to test um, whether the digit may be taken to occur equally frequently in the directory. So null hypothesis can be taken as the digit taken in the directory occurs equally frequently. Alternate will be there is no significant opposite of this. Okay, there is that means null hypothesis we have taken, there is no significance difference between the observed and expected frequency. So under S naught, null hypothesis, the expected frequency is given by what? This is the total number 10,000 from where taking sum. Okay, and average what? 10. 0 to 1, 9. How many sample? 10 sample. Okay, so average what? 1000. To find out the value of chi-square, observed value given in table in second row. This is the given one, and expected what? 1000 for every samples. So taking difference and square, we get like previous example. This is more and more greater than table value at 5% significant level. 5% significant level of chi-square test for 9 degrees of freedom. 9 degrees of freedom we get from table 16.919. Okay, since the calculated value of chi-square is more and more greater than the table value, so null hypothesis will be accepted or rejected. Please tell. Rejected, because more and more greater than table value. So there is significant difference between observed and theoretical frequencies. So the digit taken in the directory do not occur equally frequently. Okay, digit. Now another example, a little bit different to the previous three examples. Suppose records taken of the number of male and female births in 800 family having 4 children are as follows. This is actually a data. Records taken of the number of male and female in 800 families. Okay, so number of male births 0, 1, 2, 3, 4. Okay, number of female births 4, 3, 2, 1, 0. And number of families what? These types of family 32, and these types of family 178. These types of 290. Male birth, male baby and female baby. Okay, so 31 types 236 and 4094. That means no female birth. These types of family are how many? 94 families. Now you have to test whether the data are consistent with the hypothesis that the binomial law holds and the chance of male birth is equal to the of female birth. That means male birth and female births will be equal. We have to test this. Namely, total probability P equals to Q equals to what? Half. We must know. P is the probability of success and Q is the probability of failure. So there are two chances for birth. One is male baby and other is female birth. Okay. So P equals to Q equals to half is the probability and total probability 1. Now let us consider H naught is the null hypothesis. The data are consistent with the hypothesis of equal probability. That means P is for male and Q is for female, that are equal probability. The P is for male baby and Q is for not male baby, that means female. So P equals to Q equals to what? Half. We use the binomial distribution to calculate the theoretical frequency given by NR equals to capital N multiply probability of X equals to R, where N is the total number of frequency and NR is the number of families with R male children. By using normal distribution formula NCR P to the power R Q to the power N minus R. You must know this. Now for N equal for R equals to 0 and what? How many family here? N equals to the number of families with 0 male children 800. Total number N equals to what? 800 and probability of X equals to R. Okay, 4C0P to the power 4 and this will give after calculation we get what? 1 multiply 1 by 2 to the power 4 50. Now if N equals to 1, 800 multiply P to the power 1 and Q to the power N minus 1. N means what? Actually 4. Okay, so 4 minus 1 equals to 3 and N2 equals to NC2 and N equals to 4 and R equals to what? 2. This is why R equals to 2 and this is N minus 2. That means 4 minus 2. So we get 300. For N equals to, R equals to 3. Putting in this formula, we get N, capital N, and probability formula this. Okay, will give this for N equals to 3. Then R equals to 3. So N equals to 4. 4C3 half to the power R, half to the power N minus R. That means N4 will be what? This. So observed frequency, this is the in given table. Okay, expected will be what? Expected 50, 300, then 200, 300 and 800, 200 and 50. That means this is the expected. Understand everybody? So y minus ei whole square equals to what will be? This minus the whole square. This 178 minus 200 whole square. This 290 minus 300 whole square. This 236 minus 200 whole square equal to this 90 minus 50 whole square. This. So taking y minus ei whole square divided by ei expected value divided by ei. Expected value what was actually? Expected value we get 6.48 after dividing this expected value. This divided by 50 we get this. This divided by 200 we get this. This divided by 300 we get this. This divided by 200 will be this. 1936 divided by 50 will give this. So chi square equals to this form, this summation, this taking sum we get 54.433. Now comments table value of chi square at 5% significant level at 4 degrees of freedom and equals to how many samples here? Sample size 5 minus y, degrees of freedom will be 5 minus 1 equals to what? 4. So the degrees of freedom 9.49 from the table value. Understand? For the 4 degrees of freedom, table value what? 4 degrees of freedom, table value what? At 5, 9.488. Understand? This is the table value at 4 degrees of freedom, 9.488 at 5% significant level. Okay. So the table value actually less than what? Calculated value. Since the calculated value of chi square is greater than the table value, so the null hypothesis will be what? Accepted or rejected? Must be rejected because calculated value is more and more greater. The data are not consistent with the hypothesis that the binomial law holds. That the chance of male birth is not equal to that of the female birth. That means our assumption wrong. That means null hypothesis is rejected. Since the fitting is binomial, the degrees of freedom what? B equals to n minus 1. Degrees of freedom 4. Now verify whether the Poisson distribution can be assumed from the data given below. Poisson distribution. Number of defects given in first row, frequency given in second row. Suppose H naught is the null hypothesis for Poisson fit is a good fit to the data. Mean of the distribution summation fi xi divided by summation fi what? Total number of frequency what? 47 and summation fi xi fi this is the fix summation fixi will be 94. After division we get 2. Okay, this is the fi and this is the what? Xi. Now to fit the Poisson distribution we required m parameter. M equals to what? X bar. Sample mean. Understand? Sample mean m. In Poisson distribution we have we must know about m. This is the mean for Poisson distribution. Mean equals to what? 2. We have found. Now by Poisson distribution the frequency of R success, R times of success, actually how many success here? We have to verify this for number of defects what? 1, 2, 3, 4, 5. This is the 0. So 5 defects. Now we know for the Poisson distribution, for the Poisson distribution, number of R success and R equals to probability distribution function will be what? Capital N multiply e to the power minus m to the power r divided by r factorial. This is, comes from where? Poisson distribution formula. Capital N is the total number of frequency. Now for r equals to 0, 0 success, n equals to 47 e to the power m equals to what? 2. Okay, 2 and m to m means 2 to the power 0 and 0 factorial. This will give what? Approximately 6. 6.36 actually we have taken approximately 6. Now for r equals to 1, same process, same from the same formula we get 13. For r equals to 2, r equals to 2 we get this. It is near to 13. Remember 12.72 can be written as 13. For r equals to 3 we get 4.48. It is near to what? 8, 9. Now and 4 for r equals to 4 we get what? These values and this near to 4. And for r equals to 5 1.696. This is near to 2. That means we have taken whole number. Now this is the x value sample and this is the observed values given in second rows. Okay, given in second row. This is the observed frequencies. So EI equals to expected. Expected frequency what? For 0 what? 6.36. Okay. And for r equals to 1, r equals to 1 get what? 13. 13. Then for r equals to 2 we get what? 13. For r equals to 3 we get what? Near to 8. Actually this is near to 8. 8. You can take 9, but you should take near 8. And for r equals to 4, near what? 4. For r equals to 5, expected value what? 3. Now EI. EI equals to what will be? Expected value what? Expected x 6, 13, 13, 8, 4, 3. Expected value, this is fractional value, 6.36. Then what? 12.72. And this is also 12.72. And this is 8.48. And this is what? 4.24. And this is 1.696. Now this minus this divided by what? Expected value will be this. This minus this divided by expected value will be this. This minus this divided by the expected value will be this. Now taking summation using same procedure, same formula, we get chi-square equals to summation this square divided by expected value 1.2864. Taking a sum of this last row. Now the calculated value of chi-square 1.2864. The table value of chi-square at 5% significant level at degrees of freedom what? 6 minus 2, 4 degrees of freedom. 6 minus 2 what? Why? How many observed value here? 1, 2, 3, 4, 5, 6. But this is the first one is what? 0. This is why actually observed value of what? 5. So 5 minus 1, that means 4. Degrees of freedom 9.49. Hence the calculated value of chi-square is less than the table value. So H0 is accepted. So null hypothesis is accepted for the less calculated value than table value. Hence Poisson distribution provides a good fit to the data. Next, another example, the theory predicts the proportion of beans. This is the crops in the 4 groups, Z1, Z2, Z3, Z4. There are 4 groups, should be in the ratio 9, 3, 3, 1. In an experiment with 1600 beans, the number of 4 groups are this. Does the experimental results support the theory? Suppose the null hypothesis, the experimental results support the theory. We have taken the decision that the experimental result support the theory. That is, there is no significant difference between the observed and theoretical frequency under the null hypothesis. The theoretical frequency can be calculated as follows. Expected values of Z1, first group, total 100 ratio given. For first group, ratio what? 9. Multiply total divided by what? Sum of the ratio. Sum of the ratio what? 9 plus 3 plus 3 plus 1 what? 16. Okay. You must know about the ratio maths in high school. So first group expected value for the first group will be what? Total multiply ratio of first 9 first group divided by total number of total sum of the ratio. It will be 900. For the similarly for the second group, total multiply ratio of second group 3 total number sum of the ratios divided by sum of the ratios will give what? 300. Similarly for the third group, total number of beans 1600 multiply third group ratios what? 3 divided by sum of the ratio. And for the fourth, similarly total number of beans multiply fourth group what? 1 ratio 1 divided by sum of the ratio. So this will be given. So expected value how many? 4. Now observed value given, this is given in question, and expected value we have calculated First group, second group 300, third group 300, and fourth group what? Also 100. So this difference divided by EI. Okay, and whole square. We get this third row. So chi-square value what? Sum of this divided by EI. So 4.7266. So conclusion will be the table value of chi-square at 5% significant level at 3 degrees of freedom. Why? Actually 4 sample, right? This why degrees of freedom will be 4 minus 1. That means 3 difference. Is this what? 7.815. This comes from table. But our calculated value is less than the table value. Since the calculated value of chi-square is less than that of table value, hence null hypothesis will be accepted. So the experimental result is support the our theory. Now for your assignment 1, 2, 1, 2, 3, 5, 6, 5, 6, 8. This will be homework for you. Note down everybody. 1, 2, 3, 5, 6, 8, 9 will be homework for you. Okay, chi-square test as a test of independence. This is the another part for chi-square test. Actually, we're avoiding this theory. Now we'll start from examples. What are the expected frequency of 2 cross 2 contingency table given value? Actually 2 cross 2 what? 2 row 2 column. Understand? 2 row 2 column. First one is A, B and C, D, and second one is 2, 10, 6, 6. That means what are the expected? We are calculating the expected frequency by using 2 cross 2 contingency table. Now observed frequency, suppose observed frequency this is A, B, C, D is given. Understand? And here total of rows what? A plus B. Total of rows what? C plus D. And total of first column A plus C, and total of second column what? B plus D. Remember it. Now total of this or this capital N. Understand? Capital N will be found how adding the total of some row, this column or this column, anyone you can add it, then we'll get what? Total number of frequency. So expected frequency, how we'll calculate it? Expected frequency, this is expected frequency of this will be come from A plus B multiply this divided by N. Understand? We get this. And how we get this? Total of this multiply this divided by N. We get the expected value. Understand? Now this expected value, how we get? Total this total row and column, this row total, and this is the column total multiplied, cross multiplied, divided by N. N means what? This A plus B plus C plus D. Similarly, this expected value will come from this total divided multiply this total divided by total N. Understand? Using this formula. Now from this, how we can calculate it? Using this 2, 10, 6, 6. 2, 10, 6, 6. Sum will be what? Row sum. First row sum this. Second row sum 12. 6, 6, 12. And first column sum what? 2 plus 6 what? 8. And 10 plus 6 what? 16. And this is that this total or this total what? 24. This will be always same. Remember it. For any experiment, this will be always same. Now expected value how will come? Expected value for 2. This sum multiply this sum divided by whole sum. Okay. And expected value of this will be what? This sum multiply this sum divided by whole sum. Understand? The expected value of this will be what? This sum multiply this sum divided by whole sum. We get this. Now expected value of this will be what? This sum multiply this sum divided by whole sum. Understand? Now we'll try to apply this process for the solving of next example of chi-square test. Now from the following table regarding the color of eyes of father and sons, test of if the color of son's eye is associated with that of the father. That means we have test the color of eye and son. Okay, this is the eye color of son and this is the eye color of father. Light 471 and not light 51, not light 148 and not light in this case 230. Okay, now I'll test. This is the actually 2 cross 2. Now try to take the null hypothesis. The color of son's eye is not associated with that of father. That means they are independent, not depending on father. That means father's eye color, son's eye color does not depend on father's eye color. We are taking this. That means they are independent. Understand? So null hypothesis, we can calculate the expected value for each cell. Product of column total multiply row total divided by whole total. This is the eye color, light not light total, and this is the eye color of father, light not light total. Understand? So how we get this? You must know this total. This is the total, and this is also total, and this is the light total, and this is the not light total. Okay. Now how we get this expected value? This total multiply this total divided by whole total. Understand? We get this one. Now we get this expected value how? This total multiply this total divided by whole total. We get this what? This total multiply this total divided by whole total, and this expected value will be found how? This multiply this divided by whole total. So expected value are calculated for each observed value. So chi-square equals to uh, this observed value what? This observed value what? 471. Understand? Expected value what? 359.02 minus this whole square divided by expected value. So expected value second 51 minus this divided by expected value. Taking 4 sum, okay, and observed value minus this expected value divided by this expected value. Observed value last one what? 230. 230 minus this expected value divided by expected value. Okay, taking sum of this by using calculator we get 261.498. Now the calculation conclusion for the comments: the tabled value of chi-square at 5% significant level at 1 degrees of freedom. One difference. How many row column here? 2. So 2 minus 1 will be the degrees of freedom. Remember it, because there are 2 row 2 column in our given statement. 2 row 2 column. This what degrees of freedom will be what? 2 minus 1. So 1 degrees of freedom at 5% significant, the chi-square value will be what? 3.841. 3.841 at 1 degrees of freedom, 5% significant, 3.841. Remember it, this value. Okay, this value 3.841. So we get the calculated value more and more greater than the table value. 261.498 is very big number than compared to what? 3.841. Since the calculated value of chi-square is greater than more and more greater than table value, so chi-square null hypothesis will be must be rejected for greater than. That means they are dependent. That means father's eye color, son's eye color will depend on what? Father's eye color. If light, then it will be light. If not light, then it will be not light. Understand? Very interesting example. Concentration though, Shobi. Okay, next example. This is the actually how many rows here? 1, 2, 3 rows and 2 column. Okay, so the following table gives the number of good and bad parts of the product produced by the 3 shift in a factory: day shift, evening shift, night shift. Good parts, bad parts. Okay, total are given. A row total, first row total this, second row total this, third row total this. First column total this, second column total this. That means bad part total, good part total this. Grand total 2985. If we take this total sum, or if we take this two sum, will give 2985. We have to test whether or not the production of bad parts is independent of the shift on which they are produced. That means you have to verify the production of bad part is independent of the shift. Now we have taken the null hypothesis. The production of bad parts is independent of the shift on which they are produced. Okay. Now the two attributes, the production of the shifts are independent. So null hypothesis, under the null hypothesis, chi square equals to, actually there are I equals to 1. How many rows? Columns here 2, and row how many? 3. This is why j equals to 3. We have to apply this chi-square formula. Now calculating the expected frequencies. A1, B1. This is the A1, B1, first row, first column. This is the first row, first column. Okay. First row, second column. First row, second row, first column. Second row, second column. And this is what? Third row, first column. This is what? Third row, third column. How we can calculate it? Expected value what will be? This multiply, this total multiply row column total multiply divided by grand total. This how we calculate? This total multiply this divided by this. How we calculate this? This total multiply this total divided by whole total, in this way. Okay, so you can use the formula to calculate this. Okay, actually let A and B are the two attributes, namely the production and shift. A is divided into A1, A2, and B is divided into 3 parts. That means 3 row here, 2 column here. So A1, B1 will be A1 multiply B2 divided by N. Okay, A1 multiply B2 divided by N. First expected value. A1 what? 2850. 2850 grand total. And A2 B2 what? This 100. You can use this formula. Okay, same procedure as previous example. Just first to first column. This is the first row, first column. Expected value of first row, first column will be what? First row, total of first row, total of second column. Okay, divided by whole total. Now first to second column expected value what will be? What will be? First row, second column. First row total, second row total divided by whole total. First to third column what will be? First row total, third row total multiply third row total divided by whole total. Will give this. And second row first column expected value what will be? Second row total multiply first row total divided by n. And second second column what will be? Second row total multiply second column total divided by whole total will give this. So second row third column, second row total multiply third row total. Okay, divided by whole total same 45. Now we can take the classes are how many? There are 6 classes actually. 6 expected value given and 6 observed value given here. This is given observed value 960, 940, 950. This is given 960, 940. First column, second column. This is the what? First column, second column. Understand? Now expected value what will be? This is the expected value. First column, second column. Okay, first column, second column. Now just taking difference. Y minus EI. That means 960 minus 954.77 whole square. we get dividing this by what? EI, this value. This divided by this what? 0. This. Similar process, this minus this whole square equal to this, and this divided by this equals to what? This. Now this minus this what? 0. And 0 divided by this what? This 0. Similarly, we get this whole sum what? 1.28126. That means the tabled value of chi-square at 5% level of significance for 2 degrees of freedom. Now degrees of freedom for this case, what will be? Rho minus 1 multiply s minus 1. Number of row, number of column. Number of row, how many here? 3 rows, 3 minus 1. Column, how many? 2. 2 minus 1. That means 3 minus 1 into 2 minus 1, what? 2. Understand? So degrees of freedom will be what? 2. So at degrees of freedom, 2 degrees of freedom, the value of chi-square at 5% significant level, 5.991. Okay. Since the calculated value of chi-square is less than that of table value, so we accept the null hypothesis. That means the production of bad part is independent of the shift on which they are produced. We have actually calculated this value. Remember this row minus 1 multiply column minus 1, degrees of freedom formula. Row how many? Row how many here in our given row? 1, 2, 3. 3 rows given. Okay. Column how many? 2. So degrees of freedom what will be? Row minus 1, row minus 1, number of rows minus 1, number of columns minus 1 multiplied. Row how many? 3 minus 1. 3 minus 1 equals to 2. Multiply 2 minus 1. That means 1. So degrees of freedom will be 2. Remember it. Very important for you. Without this, you cannot get the table value 5.991. So applying the same procedure, example 1, 2, 3, you have to calculate. Example 1, 2, 3. Understand? And in next class, we'll give you some example like this. Okay, this is another example. Two research works classified some people in income groups on the basis of sampling studies. Their results is as follows. Poor income investigators are A and B. There are two investigators. Poor 160, 140, and total poor 300. Income group. Middle income 30 in group A, and in group B 120, and total middle 150. So reach are 10 in A sample and B sample 40, total reach what? 50. But grand total 50. Here also 50, 500, here also 500. So show that the sampling techniques at least one research work is defective. Worker is defective. Research worker. Then let us take the hypothesis that the sampling techniques adopted by research workers are similar. That means there is no difference between the techniques adopted by the research worker. This being so, the expected value of investigator classifying with the people in. So poor income group expected poor income group, what will be? Poor income group, this poor income group 300, this total multiply this total divided by whole total. Understand? Same procedure. Middle income what will be? 200. Middle income what will be? First row, this is the first row, second column, this multiply this divided by whole. In this way, rich income will be 200 multiply 50 divided by 500. So this is the actually 200 multiply 50 rich income group, 200 multiply 50, okay, divided by 500. So similarly, the expected value for B investigator, we have taken an investigator, then B investigator will be this. Now we can tabularize the observed value and expected value for chi-square test. Now group 1 for investigator A, Observed value is this. Okay, first row. This is the second row, and expected value for individual values we get this. Now just taking difference between these two, y minus ei, then taking we get this, then making a square and divided by expected value, making a square divided by this equal to this, making a square, making a square this divided by 60 what this, making a square divided by 20 this, minus 40 whole square divided by 180 will be this, 30 whole square divided by 90 will be this. Now this total sum, taking this total sum will be 55.54. Understand? Degrees of freedom what will be actually? Number of column minus 1, number of rows minus 1. Number of column how many? 3. But number of rows how many? 2. So this multiplication will be only 2. Number of column 3 in our given column. One column, first column, second column, third column. Okay. Number of column how many? 3. And number of rows, first row, second row. Number of row, total number of rows what? 2. This is why degrees of freedom can be calculated like this for using this formula. Now the table value chi-square for 2 degrees of freedom at 5% significant level is 5.99. Okay. So table value what will be for chi-square test for degrees of 2 degrees of freedom 2, what will be 5.991. Okay. 5% significant 5.991. Understand? The calculated value of chi-square is much higher. This is much higher. Calculated value is much higher than the table value, which means that the calculated value cannot be said to have arisen just because of its chance. It is significance. Hence, the hypothesis does not hold good. This means that the sampling techniques adopted by the two investigators differ and are not similar. Naturally, then the technique of must be superior than that of the other. Understand? This is another example, very important example for you. I hope these types of example you can solve. There are another example for this by using 256 times. Okay, you have coin tossed. Okay, 8 coins are tossed. This using you can calculate this. I have solved these types of example. Okay, this will be homework for you. Example 8, illustration 8, of course. Now this is also illustration 9. How many row column? 2. Degrees of freedom will be what? 1. We have solved these types of example. And example 10. Degrees of freedom given. Chi-square test also given values. Okay, thank you everybody. Today I have studied about F test and chi-square test. I hope everybody will practice it at home and understand well. So thanks to everybody.